My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 361. In this lecture, we will try to understand vector calculus. In this one, we will try to understand Grad. We will analyze, we will understand vector differentiation. What is this vector differentiation? Vector differentiation, we will try to understand Grad. Till now, we assumed that our x is scalar. That's what we assumed, isn't it? Remember, our f of x is a function which is function of scalars. What is your f of x? Function of scalars, isn't it? Now, what if x is a vector? If x is a vector. If x is a vector, because remember, in whole of machine learning or data science, we assume things to be vector. That's only way we can operate. If it is vector, you can operate in high dimensions. Isn't it? High dimensions. High dimensions. The high dimensional space, isn't it? So imagine, let's take an example. Let's take a simple example. Suppose if my y equal to, what is my y? Let me assume like this. My y equal to, let me write my y equal to A transpose x. Let's assume x is a vector. Let's assume x is a vector. What is the dimension of this vector? x1, x2, so on, xd, isn't it? Similarly, A is a vector. A is, let me say, A bar is a vector. How can I write A bar? I must write A1, A2, so on, let me say AD, isn't it? All these A1, A2, so on, AD are constants. And what does it mean? What is the meaning of y equal to A transpose x? Means y equal to summation of, how can I write? Y equal to sigma I equal to 1 to d. I can write it as AI xi, isn't it? What is this A transpose x means? How can I write? A transpose means what? I can write vector like this, A1, A2, so on, AD, isn't it? This is A transpose into x means what? X1, X2, so on, XD. This will become A1, X1 plus A2, X2 plus so on, AD, XD. This what is the meaning of y equal to I equal to 1 to DAIXI? Meaning is A1 x1 plus A2 x2 plus so on AD xd. That's what it says. Y equal to A transpose x is same as y equal to sigma I equal to 1 to DAI. This can be, I can write y equal to f of x. Therefore, I can say f of x equal to y equal to this one. Now, if I want to compute derivative of f of x, what we have to find? Derivative of f of x with derivative of f. Let me say derivative of f with respect to x. What is this x? Remember, this x is a vector. Let me say this x is a vector. This is vector differentiation, isn't it? X is a vector. This x here is a vector, not scalar. Now, how do we do it? How one can perform vector differentiation? Because we learned how to do it for scalars, but what about vector? For that, there is a special terminology. So, df by dx, if x is vector, df by dx, if x is a vector, it is often written as del of del x. del of f with respect to x, isn't it? This symbol, this is symbol, this del, what is this del? Del, this one is symbol. Just anyway, we will see, we will try to understand this. Just see this df by dx. Let me assume x is a vector, therefore I can write this del, this is known as grad, I can say, or del, isn't it? Grad, or it is often called as del. It is del f x, isn't it? Del of f. How can I read? This is del of f with respect to del of f with respect to x. So when you write this, you immediately understand that x is a vector. What does it mean? X bar is a vector and f is a function on the vector x. So typically when you write df by dx, you assume that x is scalar and f is scalar function. Typically this is the case. F is scalar function. Typically this x is scalar. This is scalar function, isn't it? Yes, x is a scalar and f is scalar function. But when you write this, when you write using grad symbol, when you write using grad or del symbol, I can say you immediately understand it is a vector differentiation. Let's understand what is vector differentiation. So del, how we can write? How we can read this one? Del f with respect to x. So del f with respect to x is nothing but, remember, x has d components, isn't it? X is a d-dimensional vector. Just try to recall what is my x. X is equal to x1, x2, so on, xd, isn't it? Now, what is my del f with respect to x? Just see, del f with respect to x, what it is? Df by with respect to x1, df by with respect to x2, df by with respect to xd. Here x is a vector, isn't it? A d-dimensional vector. So when you do vector differentiation, the resultant that you get is also a vector, isn't it? It's a vector such that first value in vector is df by dx1. What is my df by dx1? What does it mean? My first value is df by dx1. Second value is derivative of function f with respect to x2, that is df by dx2, so on and so forth. Thus this particular one, let me say this one, is also belongs to, why? Because you are with respect to x1, with respect to x2, with respect to xd means what? It also belongs to rd, means it is also a d-dimensional vector. So when you differentiate a function with respect to vector, resultant that you get is a vector which is also d-dimensional vector. So instead of writing df by dx, we often write this one, we can often write it as dou f by dou x1, isn't it? To show that that is partial differentiation, because what am I doing? I am partially differentiating f with respect to only x1, not differentiating with respect to all the components of x, isn't it? X has d components, x1, x2, so on, xd, d components. I am not using all of them. Dou f by dou x1, f is a function which has more values, isn't it? Here we are differentiating with respect to f. We are differentiating f with respect to x1. If you look at from notational perspective, del f with respect to x, this is nothing but, this is a vector. Del f with respect to x is, I can write it as in the form of dou f by dou x1. I can replace df by dx1 with dou f by dou x1, df by dx2, dou f by dou x2, which this is vector, and again this vector del f with respect to x, that is d-dimensional vector. It is belongs to r power d, isn't it? That's what this means. So let's go to the example that we had. Example that we had was f of x equal to y equal to a transpose x, that is sigma I equal to 1 to d ai xi. When I do this, what happens? So if I do grad of f with respect to x, what is the first component? Dou f by dou x1, isn't it? Just see, my first component is dou f by dou x1, my second component is dou f by dou x2, so on. My dth component is dou f by dou xt. What is f of x equal to? F of x equal to y. Just let me write it as, just let me write f of x equal to y equal to a transpose x bar, let me say, that is sigma I equal to 1 to d. This is sigma I equal to 1 to d ai xi. I can write it as a1 x1 plus a2 x2 plus so on ad xd, isn't it? Now what is my dou f by dou x1? I am differentiating f with respect to x1 partially. If I differentiate this one with respect to x1, what will I get here? x1 with respect to x1 is 1. I will get a1, all other constants. In similar manner, what is my dou f by dou x2? What is my dou f by dou x2? a2. So on. What is my dou f by dou xt? That is ad, isn't it? Therefore, I will get dou f by dou x1 a1, dou f by dou x2 a2, dou f by dou xt ad I will get. Again, I will get a vector a bar, a1, a2, so on ad. What does it mean? This is basically a bar. So, when I do partial derivative, what I get here is corresponding to dou f by dou x1, I am getting a1, and dou f by dou x2, I am getting a2. That resultant vector del f with respect to x is a bar. So derivative of a transpose, I can say derivative means del grad a transpose x. A transpose x bar, even if you want, you can say a transpose x is a bar, isn't it? That's what it says. Very, very simple. So that's what del f of with respect to x, you are getting a bar. Very, very simple. So if you think about it, if you had something like, if it is scalar differentiation, d by dx of ax equal to a, you will get a scalar, d by dx of ax equal to a. Similarly, even in the case of vectors, you will get vector a bar. Here you will get vector a bar. Here d by dx of ax equal to a means here is scalar differentiation. It's not a scalar. D by dx of ax equal to a. This is scalar. This a is scalar. So there is a lot of similarity between vector differentiation and I can say there is a lot of similarity between vector differentiation and scalar differentiation. But the most important thing is you have to note that a bar is here. A bar is a vector. This a bar is a vector. It is not scalar. Remember our logistic laws. What is our logistic laws? What is logistic laws means? Just to try to recall our previous classes about logistic laws. Remember our logistic laws. If you remember, how can I write this logistic laws function? Let me write. Yes. Let me write like this. My logistic laws is here. Let me write. Yes, I will write. Yes, my logistic laws L equal to sigma I equal to 1 to n log of 1 plus exp of minus yi into w transpose xi. This is my logistic laws, lambda into w transpose w. This is L2 regularization. Actually, what is this? This is L2 regularization. If someone is not having an L2 conceptual understanding on regularization, I will discuss. term being this is L2 regularizer. This is what my logistic loss function with the regularization looks like, isn't it? Remember here xi yi are constants. Here xi yi are constants. I can say xi yi are constants. What does it mean? Are constant because they are coming from training data. They are coming from training data, isn't it? That you have already been given. Here the vector is w. One must understand here vector is w is a vector. The variable here is, you have L is a function of w. I can say, what is this L? L is a function of w. Now to find maxima and minima for this, just try to understand there is L2 regularizer, there L of w. Now you have to perform, you have to find what you have to do, what you have to do here. Your L is a function of w. Now to find maxima and minima for this, you have to perform derivative of L or grad of L, isn't it? Grad of L with respect to w, because w is a vector here. That's why I'm writing this notation. So when I write this notation, let's see how we can compute. Let's take this term first. Let me take this particular term, lambda into w transpose w, isn't it? It is just like this is just like w square. Just refer my vector dot product lecture. You can understand. You can write it as w square, isn't it? You think that for a second, what is this? For a second, forget about w is a vector. Think this like if it is equal, just w transpose w is w square. What is the differentiation of lambda into w square? You have to, as w is a variable, you have to differentiate with respect to w. Therefore, what will you get if I differentiate with respect to w? D by dw of lambda into w square is equal to 2 lambda w, isn't it? Now let's go back to the vector equation. If w transpose w is a vector, I will also get a vector at the end of 2 lambda w. Here w is a vector. How can I find what we have to do? Just let me find this one. Which one? Let me find this del of L with respect to w. What will I get? It is simple and straightforward. Chain rule I have to apply. How can I apply chain rule? If I differentiate with respect to w first, what will I get here? Just let me erase little bit here. Yes, let me write this function again. L equal to, if I speak strictly, this is function of w, L of w, L2 regularizer, sigma I equal to 1 to n log of 1 plus exp of minus yi into w transpose xi, isn't it? Yes, plus lambda into w transpose w. Now let me differentiate, vector differentiation. How can I do this vector differentiation? Del of L with respect to w. What will you get here? Inner part. If I differentiate with respect to w, I will get minus yi into xi I will get, isn't it? Again, e power x differentiation is e power x. This is inner one. One differentiation of 1 is 0. 0 plus, what will I get here? exp of minus yi into w transpose xi, isn't it? Yes. Now let me say like this, by again log x differentiation is 1 by x. Therefore, I will get 1 plus exp of minus yi into w transpose of xi, isn't it? Plus this is lambda into w square. You will get lambda into 2w, isn't it? This is vector differentiation. Yes. Now this I need to equate this one to 0, isn't it? Now I must equate del of L with respect to W equals 0. Solving this is very, very difficult. Solving this is very, very difficult. You cannot, it's difficult to solve, isn't it? Solving this is not trivial. Here W is a vector. Solving this is not trivial, and here we will learn computational techniques or programmatic techniques called gradient descent. Yes, the gradient descent techniques to solve these problems very intuitively. We will try to understand what is gradient descent in my next lecture. In my next lecture, we will try to understand geometric intuition behind this gradient descent algorithm. Time being, just understand this is a regularizer. This regularizer is a function of W. Now this is where W is a vector. I have to find maxima or minima. I have to find vector differentiation. Just we are differentiating vector differentiation. But to solve this problem, it's very difficult to solve. It is very cumbersome process, difficult process. Therefore, there is a technique. What is the technique? The technique name is called gradient descent technique, which is used to solve this particular equation. In my next lecture, I will discuss about gradient descent algorithm. Thank you very much.